Hello Noddies, welcome back to the channel. In today's video, we are going to understand one of the most important concept in analog, RF and communication system, the impedance matching. Whether you are designing an antenna, a RF amplifier, a mixer, a PLL, or even a high-speed interface, impedance matching plays a very critical role. In today's video, we will understand what is maximum power transfer, why reflection occurs, why don't we simply use resistors for matching, how inductor and capacitor are used, and how to actually design a L matching network. Now let's get started. Let's start with the simple source and load. According to maximum power transfer theory, the maximum power is equal to voltage square by 4 times of source resistance. For maximum power transfer, the load impedance must match the source impedance. For purely resistive circuits, the source resistance should be equal to the load resistance, and for the purely reactive circuits, the source impedance should match with the load impedance. Now let's understand this using a real life analogy. Imagine two people carrying water buckets. One person is pouring water in another bucket. If both buckets are of similar size, almost all the water gets transferred smoothly. But if one bucket is extremely small, the other becomes extremely large, the transfer becomes inefficient. Similarly, when source and load impedance are matched, power transfers efficiently. When they are mismatched, power transfers reduce. Here let's take an example. Here if the source and load resistance are equal, then the maximum transfer is around 0.5 watts. Here if the source and load are mismatched, then the power across the load is only 9.9 milliwatts, which is very much lesser than maximum power. So we are going for this impedance matching technique where the maximum power that is delivered should be absorbed by the load effectively. And there is another important issue, which is the reflections. The reflection coefficient is given by this formula, and if RL is equal to RS, then there is no reflections. If RL is not matched with the source resistance, then there is a reflection. Reflection is nothing but when you try to transfer a signal, some of the signal bounce back to the original source, which we don't actually want. We want all the signals that is transferred from the source to be absorbed by the load. So that's the other reason we go for this impedance matching techniques. At this point you may think, why not simply add resistor and make the values equal? Here if you want to match the 50 ohm source with the 1000 ohms load, you can either increase the RS or decrease the RL. For example, you could add a resistor in series with the source resistor to match with the RL, or you can add a resistor in parallel with the RL to match it with the RS. But this won't practically work out. Let's understand why. Imagine if you are transferring water between two tanks. Would you intentionally create leaks in the pipe to make the flow look correct? Of course not, right? The water would simply be wasted. That's exactly what a resistor does. Here you could see there is around 20 milliamps flowing from the source, but the major of the current is passed through the 50 ohms resistor, where only 2 milliamps is passed through the 10 kilo ohms resistor, wherein we want the maximum power to be transferred only to the load and not to any other component. Hence, we can't use resistor for the matching purposes, so we go for inductor and capacitor who can store and release energy. Now let's try to design one. Here suppose if RL is greater than RS, we use L network consisting of one series reactance and one shunt reactance. The first step is to transfer the load resistance. Here we are keeping a reactance term in parallel with the resistance term to reduce the resistance of the load. The second step is to cancel the unwanted reactance which is introduced by this newly introduced component. It can be easily cancelled out by introducing another series reactance. Finally, we force the input impedance to be equal to the source resistance. So after solving the equations, we could separate them into real and imaginary terms. And by equating the real term and the imaginary terms to zero, we could actually obtain the formula for series reactance term and the parallel reactance term. And similarly, if the load is lesser than the source resistance, this would be the formula. Now let's try to match this. Here the source resistance is taken as 50 ohm while the load resistance is taken as 10 kilo ohms. We have to match it at 2.4 GHz frequency. As you know, 2.4 GHz is a Bluetooth frequency. Now substitute these values in the formula to get your XS value and substitute this XS in the second formula to get your XP value. Now we can choose between two circuit choices. One is the series inductance and parallel capacitance, and another is the series capacitance and parallel inductance. So for the first circuit, choose the series element as inductor. Now xs is equal to omega L. Now substituting the values, we get the inductance to be 46.8 nanohenry. And similarly for the parallel, we choose the element to be capacitor. Now plugging in the values, we get the capacitance around 93.5 femtofarad. You can actually try the circuit yourself. This is the formula that is required for you to design the second circuit. And the one more another important thing to notice here is the quality factor. For this matching network, the quality factor is around 14.1. Here the quality factor is very high, hence we can expect a very lower bandwidth, and this is the expected graph. Now let's try to simulate this in Cadence and see whether we got a required value. Open your Cadence, press I to go to add instance window. Here find your inductor from the analog library. Our inductor is found to be 46.8 nanohenry. Place your inductor, press I again to go to the add instance window. Find your capacitor. Our capacitor is found to be 93.5 femtofarad. Place your capacitor. Here find your resistor. Our load resistor is set to be 10 kilo ohms. So place your resistor here. Press R to rotate your inductor. Press I to go to the add instance window. Here find your port. Here the port resistance is set to be 50 ohms, which is our source resistance. So leave it the same. Give the amplitude 1 as 1 volt and the frequency 1 as 2.4 gigahertz, which is our input frequency. Place your port. Press I again. Find your ground from the same analog library. Place your ground. Press W to finish wiring your circuits. Here I have finished wiring my circuits. Check and save. Launch. ADL. Here choose your analysis as SP, which is S parameter, which we will explain in the next video why we are going for this S parameter analysis. Now click select, click your input port. Here give your start as 1 gigahertz and the stop as 3 gigahertz. Since we are going to check it for 2.4 gigahertz, this range is much more optimum. Click OK, run your simulation. Result, direct plot, main form, TB20 and press S11. So from this we can see at 2.4 gigahertz we can see a minus 64 dB, which actually tells us that there is no signal that is transferred back to the source. Here, as less as the dB gets, that much of the impedance matching has been occurred. Here we got minus 64 dB, which implies that it is a very good impedance matching network. Here we got a required graph and verified it using the cadence. So Noddies, in today's video we learned about the maximum power transfer, reflection coefficient and why impedance matching is important. In the next video we will go one step further and explore what is pi matching, what is T matching and why we use the S parameter analysis in our cadence. So until then Noddies, keep learning, keep simulating and keep building.